Greetings, everybody. Learning as a hobby here. I want to go over my solutions to selected exercises from Spivak's calculus in chapter 9. So let me bring those up. And as usual, usually in Spivak, I don't do all the problems in the exercise set just because there's so many of them. So usually I pick the ones that look like they're important for later sections or just ones that look interesting to me. So we'll start with question number 4 here, um, which says, for each natural number n, let Sn of x equal x to the n. And remembering the formulas for S1, S2, S3 that we derived in my chapter summary for chapter 9, if you want to look back at that video, which you should look at before you look at the video here. Conjecture a formula for Sn prime of x and prove your conjecture. So my conjecture is the well-known power rule for um, derivatives of monomials. All right, here's the proof. Let n be a natural number. Consider the limit as h goes to 0 of the difference quotient for Sn. That's equal to the limit as h goes to 0 of x plus h to the n minus x to the n over h. And then we can expand x plus h to the n using the binomial theorem, which I did on the next line. Excuse me. All right, and that's equal to limit h goes to 0 of summation k going from 0 to n choose k, x to the n minus k, h to the k minus x to the n, and that's all divided by h, of course, equals limit h goes to 0. So here I simplified, and that gives you summation k going from 1 to n choose k, x to the n minus k, h to the k minus 1, and then just breaking up the sum into a more convenient form. That's the same thing as limit h goes to 0 and choose 1, x to the n minus 1, plus, and then you can factor out a common factor of h from all the remaining terms in the polynomial. So you get plus h times summation k equaling 2 to n, and choose k, x to the n minus k, h to the k minus 2. And then finally, you can take the limit, which gives you n choose 1, x to the n minus 1. And of course, n choose 1 is equal to n, and that gives you the formula. All right. Question number 5 says, find f prime if f of x is the floor function of x. And here's my solution. If x is not an integer, then f prime of x is 0. So we only need to consider when x is an integer. Let x be an integer. Then if we look at the one-sided limits and you do the calculation here, notice that the one-sided limits don't agree with each other. So if you approach from the right-hand side of 0, then the limit is 0. Whereas if you approach from the left, you get positive infinity. Therefore, f prime does not exist when x is an integer. So f prime of x equals 0, except for when x is an integer. All right, question number 6. Prove starting from the definition and drawing a picture to illustrate. There's a lot of questions here that ask you to draw the picture. I just didn't draw the pictures, but I'll explain, hopefully intuitively, it'll make sense what I'm trying to say here. But also, you could draw the picture yourself and it should make sense. Part A says if g of x equals f of x plus c, then g prime of x equals f prime of x. This should make sense because f prime of x plus c is just a translation either upward or downward by c units of the graph of f. So the graph of g and f should be parallel at any x value, right? The tangent line, I mean, to g and f should be parallel at any x value. That's what g prime equals f prime means. So here's the proof. G prime of x equals the limit h goes to 0 of f of x plus h plus c minus f of x minus c all over h. And then when you simplify, you get the derivative of f. Right? Part B says if g of x equals c f of x, then g prime of x equals c times f prime of x. Right? And, similar type of idea. If g is c times f of x, then it's either a vertical stretch or a vertical shrink of the graph of f. So the derivative should be related in a similar manner. Right, here's the proof. G prime of x, again, using the formula for the derivative, is limit h goes to 0, c of f of x plus h minus c f of x all over h. You can factor out the common factor of c, times the limit of f of x plus h minus f of x over h, which is c times the derivative of f. Okay, question number 7. Suppose that f of x is x cubed. Then in part A, he asks us to calculate a few values for f prime. So we want to calculate f prime of 9, f prime of 25, and f prime of 36, which I do down here, which you can look at. In part B, he asks what is f prime of 3 squared, f prime of 5 squared, f prime of 6 squared, and of course, these values are the same. And then finally in well, not finally, there's one more part after part C, but he asks what is f prime of a squared and what is f prime of x squared? And f prime of a squared is 3a to the 4. F prime of x squared is 3x to the 4. And then for the next part, he has this little explanation here. If you don't find this problem silly, you're missing a very important point. F prime of x squared means the derivative of f at the number, which we happen to be calling x squared. It is not the derivative at x of the function g of x equals f of x squared. But to drive the point home, in part D, he says for f of x equals x cubed, compare f prime of x squared and g prime of x, where g of x is f of x squared. So this is sort of like one of the questions on sort of the vagary of the notation that we have for derivatives. But you can see the difference here, so you got to be a little bit careful. F prime of x squared, we said already up above in part C, was 3x to the 4, whereas g of x equals f of x squared, which is x squared cubed, which is x to the 6. So if we take the derivative of g with respect to x, we get 6 times x to the 5. Clearly, those two functions are not the same. All right, question 8, part A. Suppose g of x is f of x plus c. Uh, that means that g of x is actually a horizontal translation of the graph of f, either to the right or to the left. Proofs starting from the definition that g prime of x equals f prime of x plus c, and draw a picture to illustrate this. Again, I didn't draw the picture, but just intuitively think about it like this. If the graph of g is the graph of f shifted horizontally by c units to either the right or the left, then the tangent lines to g should be parallel to the tangent lines of f, but shifted to the right by c units or to the left by c units, right? Um, to do this problem, you must write out the definition of g prime of x and f prime of x plus c correctly. Again, just to make it clear of the vagaries of the notation that we have for derivatives and to be careful. The purpose of this problem, sorry, the purpose of problem 7 was to convince you that although the problem is easy, it's not an utter triviality, and there is something to prove. You can't simply put prime marks into the equation g of x equals f of x plus c. To emphasize this point, see part B, but let's do part A first. Here's the solution. G prime of x, using the definition, is the limit of the difference quotient as h goes to 0, which is equal to the limit as h goes to 0 of f of x plus h plus c minus f of x plus c over h, and then just rearranging things. That's the same thing as limit h goes to 0 of f of, in parentheses, x plus h, x plus c plus h minus f of x plus c over h, which is obviously the derivative of f at x plus c. Right? Part B, prove that if g of x equals f of c of x, then g prime of x equals c times f prime of cx, and try to see pictorially why this should be true. Again, I didn't draw the picture, but just again, think about what the transformation does. F of cx is either a horizontal stretch or shrink, depending on the magnitude of c. Then the tangent line will be stretched either vertically or horizontally, depending on uh, where the where x is, I guess, right? So if you stretch the graph of f horizontally, then the graph of g is going to be wider than the graph of um, is going to be wider than the graph of f. And because vertical and horizontal translations sort of work in the opposite sense from each other, if you're stretching horizontally, that's a shrink vertically. So it should make sense that g prime should be c times f prime of c of x. Again, if that's kind of confusing, you could draw the picture and you'll see what I'm saying. Okay, so again, here just do use the definition of the derivative, g prime of x equals limit h goes to 0 of the difference quotient of g, which is the limit h goes to 0 of f of cx plus ch minus f of cx over h, which is equal to limit h goes to 0 of, now here what I did was I multiplied by c over c, which is like multiplying by 1, so it doesn't change the value. I can factor out a factor of c out in front of the limit by the rules of limits. So that's equal to c times limit f of x cx plus ch minus f of cx all over ch, and that's the derivative of c. Sorry, that's c times the derivative of f prime evaluated at cx. All right, part C says, suppose that f is differentiable and periodic with period A, or in other words, f of x plus a equals f of x for all x. Prove that f prime is also periodic. So we'll let g of x equal f of x plus a, then g prime of x equals f prime of x plus a by part A. Also, g of x equals f of x plus a, which is equal to f of x because f is periodic, right? For all x. So g of x equals f of x equals implies g prime of x equals f prime of x. Therefore, f prime equals g prime equals f prime of x plus a for all x. Therefore, f prime is periodic with period a, right? Because f prime of x equals f prime of x plus a for all x. Okay, question 11. There's a few parts to this too. Part A says, prove that Galileo was wrong. If a body falls a distance s of t in t seconds and s prime is proportional to s, then s cannot be a function of the form s of t equals ct squared. Sorry, I just wanted to check something on the screen here. Okay, here's my proof. Let s prime of t equal k s of t, meaning, we're assuming that s prime is proportional to s of t. Then s double prime of t equals k times s prime of t, which is equal to k squared s of t by some of the things that we've already proven. However, if s of t equals ct squared, then s double prime of t equals 2c. This implies that 2c equals k squared s of t, or in other words, s of t is the constant function with value 2c over k squared. But this contradicts that a falling body's position changes with time, right? It doesn't make sense. So that's a contradiction. All right, part B, prove that the following facts are true about S if S of t equals a over 2 t squared. The first fact will show why we switched from c to a over 2. So here's the first fact, S double prime of t equals a, or in other words, acceleration is constant. And again, here's the proof. You just take the derivative using the formula that we derived in question number 4, I think it was. Let S of t equal a over 2 t squared, then S prime of t is a over 2 times 2t, which is at, and S double prime of t equals a. So that shows that the acceleration is constant. And fact number 2, s prime of t squared equals 2a s of t. And again, you just, plug in the formulas. So s prime of t all squared is at squared, because we know that s prime is at, which is a squared t squared. And if you calculate 2a st, you get the same thing. So it checks out. All right, question number C. Maybe this one is relatively straightforward. It's just plugging in numbers into formulas and solving equations. So maybe I'll just actually skip going over this one in the video. You can, stop your screen if you or pause your screen if you want to watch if you want to look at the solution here. But there's nothing particularly interesting about that one. So let me skip that and go to question 12. Imagine a road on which the speed limit is specified at every single point. In other words, there's a certain function L such that the speed limit X miles from the beginning of the road is L of X. Two cars A and B are driving along this road. Car A's position at time T is A of T, and car B's is B of T. And then there's a bunch of questions here. So part A says, what equation expresses the fact that car A always travels at the speed limit? He gives a hint here in the book. He says the answer is not A prime of T equals L of T. In fact, the solution is A prime of T equals L of A of T, right? Because A of T gives you the value of X at time T. All right, part B, suppose that A always goes at the speed limit and that B's position at time T is A's position at time T minus 1. Show that B is also going at the speed limit at all times. So let B of T equal A of T minus 1 and A prime equal L of A of T. Then B prime of T is A prime of T minus 1, which is equal to L of A evaluated at T minus 1, which is L of B of T. Right? Part C, suppose instead B always stays a constant distance behind A. Under what conditions will B still always be traveling at the speed limit? So solution, let C be a positive constant and B of t then would be A of t minus C. So, B of t is always behind t by the same distance, right? And A prime of t equals L of A of t because A is always traveling at the speed limit. Then B prime of t is A prime of t, which implies B prime of t equals L of A of t minus C must be satisfied in order for B prime of t to equal L of B of t. All right, question number 13. Suppose that f of a equals g of a and that the left-hand derivative of f at a equals the right-hand derivative of g at a. Define h of x equals f of x for x less than or equal to a, and h of x equals g of x for x greater than or equal to a. Prove that h is differentiable at a. So we just calculate the the one-sided limits and just show that you get the same value, which I did here. So I won't, you could pause your screen. I won't belabor this. It's relatively straightforward. Question number 14. Let f of x equal x squared if x is rational and f of x equals 0 if x is irrational. Prove that f is differentiable at 0. So here, 0 equals limit h goes to 0 of 0 over h less than or equal to limit h goes to 0 f of h over h less than or equal to limit h goes to 0 of h squared over h, which is equal to limit as h goes to 0 of h, which of course is 0. That implies that the limit of f of h over h as h goes to 0 is 0 by the squeeze theorem, right? Implies f prime of 0 equals the limit as h goes to 0 of f of 0 plus h minus f of 0 over h, which equals limit h goes to 0 of f of h over h when you simplify everything, which equals 0. And that proves the statement. F of 0 is irrational. Yeah, okay. Sorry, I just wanted to double check something. Okay, 15, part A. Let f be a function such that the absolute value of f of x is less than or equal to x squared for all x. Prove that is differentiable at 0. If you have done the problem 14, you should be able to do this. So here's the proof. Absolute value f of x less than or equal to x squared implies 0 less than or equal to absolute value f of x over x less than or equal to x squared over absolute value x, which is less than or equal to absolute value x for all x not 0. And that implies that 0 less than or equal to limit of the absolute value of the difference quotient at 0, which is equal to the limit h goes to 0 f of h over h less than or equal to limit absolute value h as h goes to 0, which is 0. And then that shows that f prime of 0 is 0. All right, part B, this result can be generalized if x squared is replaced by absolute value g of x, where g has what property? So here's my solution. It must be the case that limit x goes to 0 of absolute value g of x over x equals 0 and g of 0 equals 0, so that the absolute value f of 0 is less than or equal to the absolute value of g of 0, which is 0, which implies that f of 0 is 0, and that the limit as h goes to 0 of absolute value of the difference quotient evaluated at 0 is equal to the limit as h goes to 0 of absolute value f of h over h less than or equal to limit h goes to 0 g of h over h, which is 0. So that's question 15. All right, question 16, let alpha greater than 0 if f satisfies absolute value f of x less than or equal to absolute value x to the alpha. Prove that f is differentiable at 0. All right, this follows directly from problem 15, since the absolute value of f of 0 is less than or equal to 0, the absolute value of 0 to the alpha power, which is 0, so f of 0 is 0, and limit h goes to 0 of absolute value h to the alpha over absolute value h is limit h goes to 0 of absolute value of h to the alpha minus 1, and alpha minus 1 is greater than 0 because alpha is greater than 1, so obviously that equals 0. All right, question 17. Let 0 less than beta less than 1, excuse me. Prove that if f satisfies absolute value f of x greater than or equal to absolute value x to the beta, and f of 0 is 0, then f is not differentiable at 0. So here's the proof. Let 0 less than beta less than 1, then -1 less than beta minus 1 less than 0. In other words, beta minus 1 is negative. So limit h goes to 0 of the absolute value of the difference quotient evaluated at 0 equals limit h goes to 0 of f of h over h, which is greater than the limit h goes to 0 absolute value x to the beta minus 1, which is infinite. So that shows that the limit doesn't exist. Therefore, f is not differentiable at 0. All right, question number 18. Spivak puts a star next to this problem. I forget if that means that he's going to use this problem later on in the book, or if it's means that it's considered like a more difficult problem, but let's go through it anyway. So this is question 18. Let f of x equal 0 for irrational x and 1 over q for x equal p over q in lowest terms. We've actually looked at this function in a previous chapter. Prove that f is not differentiable at any a. And Spivak gives a hint. He says it's obvious. Sorry, it obviously suffices to prove this for irrational a. He wants us to say why, and then if a equals m, so the decimal expansion of a is m decimal point a1, a2, a3 dot 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 is the decimal expansion of a. Consider the difference quotient evaluated at a for h rational and also for h equal negative 0.00 dot 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 0 an plus 1 an plus 2 dot dot dot. So, the decimal expansion of h, if a is irrational, is the part of the decimal expansion of a, the negative of the decimal expansion of a, past the nth term, I guess. Oh, sorry, the nth decimal place. All right, here's my proof. Since f is not continuous at all a in q, f is not differentiable at all a in q by the contrapositive of theorem 9.1. Theorem 9.1, if you haven't watched the video for the chapter summary yet, theorem 1 says if a function is differentiable, then it's continuous. So the contrapositive of that is if f is not continuous, then f is not differentiable. All right, so that's why you don't have to worry about rational values of a. Therefore, we only need to consider a irrational. Okay, there's a couple cases. Case 1, for all h rational, a plus h is not rational, so f of a plus h minus f of a over h is 0 over h. So the limit goes to, there should be the limit going to 0. Oops. Or actually, I could say this, the 0 over h is, for h not 0 is always 0. And then, obviously this, whoops, obviously this goes to 0 as h goes to 0. Right? Case number 2, for any a irrational, a has an infinite decimal expansion. Again, say a is m decimal point a1, a2, a3, et cetera, then for any h irrational, I'll call hn the the specified value of h that he gives in the hint. All right, then a plus hn is rational, and f of a plus hn minus f of a over hn is equal to 1 over 10 to the n h sub n, which is -1 over 0 point a n plus 1 times a n plus 2 dot 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 for on forever, because you're multiplying the decimal by 10 to the n, right? Then the absolute value of f of a plus hn minus f of a over hn equals 1 over 0 point an plus 1, et cetera, which is greater than or equal to 1 for any hk in the set of hns. So limit n goes to infinity of f of a plus 1 over n minus f of a over 1 over n. So here, 1 over n, I'm choosing natural numbers for n. That limit goes to 0, but notice if you take the limit as n goes to infinity of f of a plus hn minus f of a over hn, that's greater than or equal to 1. So therefore, the limit doesn't exist. Right? All right, question number 19 also has a couple parts. Part A says, suppose f of a equals g of a equals h of a. such that f of x less than equal g of x less than equal h of x for all x, and that f prime of a equals h prime of a. Prove that g is differentiable at a, and that f prime of a equals g prime of a equals h prime of a. Spivak says begin with the definition of g prime of a. Here's my proof. F of a plus h less than g of a plus h less than equal h of a plus h. That's part of the hypotheses, right? Implies f of a plus h minus g of a less than or equal to g of a plus h minus g of a less than equal h of a plus h minus g of a. But then g of a is equal to f of a and g of a is equal to h of a. So you get the next line, divide everything by h, and that inequality holds for all those difference quotients if h is positive, and if you take the limit as h approaches zero from above, you get that f prime of a is less than or equal to the the one-sided derivative, right? The right-hand derivative of g is less than or equal to h prime of a, and a similar thing happens if you let h approach zero from below. If h is negative or less than zero, then the difference quotients all still satisfy similar inequality, but with the inequality symbols reversed. And then when you take the limit as h goes to zero from below, you get the same relationship here. Well, similar type of relationship here. F prime of a is on top and g prime of a is in the bottom. But that implies that since the two limits, the two one-sided limits agree with each other, that means that the derivative of g evaluated at a is a f prime of a and g prime of a, or sorry, and h prime of a. All right, so part B, show that the conclusion doesn't follow if we omit the hypothesis f of a equals g of a equals h of a. I just came up with a counter example here. So let f of x be x squared, h of x equal x squared plus 1, and g of x be the function where x squared plus 1 half is the output when x is not 0, and the output at 0 is 0. These three functions satisfy the hypotheses, except for the one that they're saying, we want to throw out. And notice that the derivatives here don't have the relationship in part A, namely g of x isn't even differentiable at 0. All right, question number 20. Let f be any polynomial function. We'll see in the next chapter that f is differentiable. The tangent line to f at a, comma f of a is the graph of g of x equals f prime of a, x minus a plus f of a. Thus f of x minus g of x is the polynomial function. D of x equals f of x minus f prime of a times x minus a minus f of a. We have already seen that if f of x equals x squared, then d of x equals x minus a squared. And if f of x is x cubed, then d of x is x minus a squared times x plus 2a. We showed those in the chapter summary. So again, you should watch that video before you look at this one. Part A says find d of x when f of x is x to the 4 and show that it is divisible by x minus a squared. So I just wrote everything out here. You get d of x, you get the polynomial x to the 4 minus 4a cubed times x minus a to the 4, which you can rearrange, and then you end up factoring out a common factor of x minus a, and then here I did synthetic division to factor out another factor of x minus a from the cubic here. So indeed, d of x is divisible by x minus a squared. So when you factor it, you get x minus a squared times x squared plus 2ax plus 3a squared. All right, part B then says there certainly seems to be some evidence that d of x is always divisible by x minus a squared. And he says figure 22 provides an intuitive argument. I won't show the picture here, but it's in the book. Usually lines parallel to the tangent line will intersect the graph at 2 points. The tangent line intersects the graph only once near the point, so the intersection should be a quote-unquote double intersection. To give a rigorous proof, first note that d of x over x minus a equals f of x minus f of a over x minus a minus f prime of a. Now answer the following questions. So there's a bunch of questions here he wants us to answer. Why is f of x minus f of a divisible by x minus a? Why is there a polynomial function h such that h of x is d of x over x minus a for x not a? Why is limit x goes to a of h of x equal to 0? And why is h of a equal to 0? And finally, why does this solve the problem? So I just took each of those one at a time. All right, the answer to question 1 is f of x minus f of a is divisible by x minus a because f of x minus f of a is a polynomial that has root a, right? If you plug a in for x, you get f of a minus f of a, which is 0. In other words, well, I just said that here, f of a minus f of a is 0. So that means that x minus a is a factor of that polynomial. Right? The answer to question 2, f of x minus f of a minus f prime of a times x minus a is a polynomial with root a. So d of x equals f of x minus f of a minus f prime of a times x minus a has x minus a as a factor. Similar reason as to part 1. Question number 3, limit h of x goes to 0 as h goes to a, since limit x goes to a of h of x equals limit x goes to a of d of x over x minus a is equal to limit x goes to a of f of x minus f of a over x minus a minus f prime of a, which is f prime of a minus f prime of a, which is 0. So the limit there goes to 0. Question number 4, h of a is 0 since h of x is a polynomial and therefore continuous. So the limit equals the function value there. So 0 equals limit x goes to a of h of x equals h of a. And finally, since a is a root of h of x and h of x is a polynomial, x minus a is a factor of h of x. So h of x over x minus a is d of x over x minus a squared, which is a polynomial, which means that x minus a squared is a factor of d of x. And that proves the statement. All right, question number 21. Part A says, show that f prime of a is limit x goes to a of f of x minus f of a over x minus a. Here's the proof. If x is not a, then there's some h in R with x is a plus h. So f prime of a equals limit h goes to 0 of f of a plus h minus f of a over h, which is equal to limit h goes to 0 of f of x minus f of a over a plus h minus a, which is limit h goes to 0 of f of x minus f of a over x minus a, and that's it. Part B, show that derivatives are a quote-unquote local property, meaning that if f of x equals g of x for all x in some open interval containing a, then f prime of a equals g prime of a. This means that in computing f prime of a, you can ignore f of x for any particular x not a. Of course, you can't ignore f of x for all such x at once. So here's the proof. Let alpha beta be an open interval containing a and f of x equal g of x for all x in the interval. Then for all x in the interval, the limit x goes to a of f of x minus f of a over x minus a is equal to limit x goes to a of g of x minus g of a over x minus a. And that implies f prime of a equals g prime of a. This follows from rules of the limit. This follows from rules of limits that we looked at. And I think we did it in chapter 5. So question number 23, prove that if f is even, then f prime of x equals negative f prime of negative x. In order to minimize confusion, let g of x equal f of negative x and find g prime of x, and then remember what other thing g is. Again, he says draw a picture, but what this is saying is that we want to show that the derivative of an even function is an odd function. And actually in question 24, we want to show that the derivative of an odd function is an even function. So there's geometry there. I didn't draw the picture, but again, if you think about the symmetries inherent in even and odd functions, this should make sense. All right, here's my proof. Let f be even and let g of x equal f of minus x. Then the limit as h goes to 0 of g, the difference quotient for g, that equals the limit as h goes to 0 of f of minus x minus h minus f of minus x over h. Here I multiply by minus 1 over minus 1, which doesn't change the value. So, but then I can factor out a minus out in front of the limit, which gives us negative limit h goes to 0, f of minus x minus h minus f of minus x, all divided by minus h, which is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. That's because f is even, right? Then minus f prime of minus x is equal to g prime of x, which is equal to f prime of x. And that shows the relationship. So the derivative of an even function is odd. right? Then we'll do something similar for proving that the derivative of an odd function is even. So it's very similar to the one we just did. So if you want to pause your screen and look at my proof, you can look at it, but I won't because it's very similar to the one we just did. So I'll just skip going over that here. Question 25 says problem 23 and 24 say that f prime is even if f is odd and odd if f is even. What can therefore be said about f, the kth derivative of f? And from the formulas, if f is even, then the kth derivative of f at x is -1 to the k, f to the k evaluated at minus x, and f is odd implies that the kth derivative of f at x is -1 to the k plus 1 times f, the kth derivative of f evaluated at minus x. All right, question number 27. If Sn of x is x to the n and k is between 0 and n, including the endpoints, prove that Sn of the kth derivative of Sn of x is n factorial over n minus k factorial times x to the n minus k, or another way of writing that is k factorial times n choose k x to the n minus k. The proof is by induction, so fix an n in n and induct on k. The base step is simple. If k equals 0, the 0th order derivative of Sn at x is just the function itself, and that's obviously equal to 0 factorial times n choose 0 times x to the n minus 0, right? 0 factorial, if you remember, is defined to be 1, and n choose 0 is 1, and obviously n minus 0 is n. All right, so we go on to the inductive step. Assume the kth derivative of n of x is k factorial times n choose k, x to the n minus k for some k greater than or equal to 0 and less than or equal to n, and consider the k plus first derivative of Sn at x. That's the same thing as the kth derivative of Sn derivative, right? The derivative of that evaluated at x, which by the inductive hypothesis is k factorial, and choose k times x to the n minus k minus 1, and then times n minus k by the power rule, right? By inductive hypothesis. So k factorial, n factorial over k factorial, n minus k factorial times n minus k times x to the n minus k minus 1. Here you can multiply the top and the bottom by k plus 1 and by n minus k minus 1. And when you simplify everything, you end up with what you want. So you get k plus 1 factorial and choose k plus 1 times x to the n minus, in parentheses, k plus 1. So the theorem follows from induction. All right, question 28, part A. There's only a couple more questions that I did here. Find f prime of x if f of x is the absolute value of x cubed. Find f double prime, and does f triple prime exist for all x? So again, you just use the definition. So here I'm taking the limit of the difference quotient as h goes to 0. You can factor out, right, the difference of two cubes factors into absolute value x plus h minus absolute value x times absolute value x plus h squared plus absolute value x times absolute value x plus h plus absolute value x squared, and that's all divided by h. But x plus h minus absolute value x plus h minus absolute value x over h is either plus or minus 1 depending on whether h is positive or negative. So the cases that you end up with are here. If x is greater than or equal to 0, then f prime of x equals 3 times the absolute value of x squared, which is equal to 3 x squared. And if x is less than or equal to 0, then f prime of x equals -3 times absolute value x squared, which is minus 3x squared. So you get this the derivative written in this piecewise fashion here. And then, you could just keep going. The second derivative here is defined for all real numbers. It's 6x if x is greater than or equal to 0, -6x if x is less than or equal to 0. However, if you try to take the third derivative at 0, notice here if I take the one-sided limits, they don't agree. So the third derivative is not differentiable. Sorry, the third derivative doesn't exist at 0, or in other words, the second derivative is not differentiable at 0, but for every other value it is. If x is positive, the third derivative is 6. If x is negative, the third derivative is minus 6. Right, in part B, Spivak says analyze f. Similarly, if f of x is x to the 4 for x positive and f of x equals negative x to the 4 for x negative or 0. And similar type of thing happens here. I won't belabor this. You can pause your screen and see what the case is. And then last question here, question number 29. Let f of x equal x to the n if x is greater than or equal to 0, and let f of x equal 0 for x less than or equal to 0. Prove that the n minus first derivative of f exists and find a formula for it, but that the nth derivative of f evaluated at 0 does not exist. And it's similar type of reasoning. So if you take the n minus first derivative of f at x, you get n factorial times x for x greater than or equal to 0, and you get 0 if x is less than or equal to 0. But if you take the one-sided limits of uh, the difference quotient for the n minus first derivative of f, approaching 0, you get 0 if you approach from the left, if you let x approach 0 from the left, and you get n factorial if you let x approach 0 from above. Obviously, the one-side limits there don't agree, so the limit doesn't exist at 0, which means that the nth derivative of f at 0 doesn't exist. However, for all of the values of x, the derivative does exist. So the nth derivative of f at x is n factorial if x is strictly greater than 0, and 0 if x is less than 0. Okay, so let me stop my screen share here. That's the last question that I did in the section. Like I said, Spivak has a lot of exercises in each of his chapters, so that was a bunch of them. Hopefully, this video wasn't too long, but let me know what you guys think down below, and give me a like and subscribe if you enjoy the content. And I'll see you guys in the next one.